Good morning, everyone. My name is María Alejandra Cornejo. I am a computer science student of Universidad Católica San Pablo from Peru. Today I will going to present our paper entitled Categorization of Simultaneous Localization and Mapping Knowledge for Mobile Robots. This is important because nowadays autonomous robots are playing important roles in everyday life activities, as well for academic, technological, and scientific applications. So I will start by explaining the area of knowledge that we want to organize with this proposal, SLAM. This is the acronym for Simultaneous Localization and Mapping. It is a chicken egg problem because the two tasks that have to be done are codependent. Since localization is about inferring location given a map, and mapping is about inferring a map given location, then SLAM is a combination of these two tasks because it's about learning a map and locating the robot in this map simultaneously. This SLAM problem has been solved in many ways and by various types of robots. For example, on the top left of this figure, there is the Pioneer 3DX, used for testing SLAM algorithms. On the right, a panoramic view of the robot environment. This image is captured by the camera located on the front of the Pioneer. After applying SLAM algorithms, we can see the results on the bottom of the figure. On the left side, we have a CAD model of the environment, where the red line represents an estimated robot trajectory. On the right side, accumulated 3D point clouds, where light blue, pink, and green points represents the obstacles mapping by the robot during the SLAM process. Additionally, there are estimated robot poses in yellow points. Although SLAM is a widely studied problem in robotics, there is still a lack of standardization to represent that information and the knowledge needed to propose efficient and interoperable solutions. In this sense, it is evident the necessity of a well-defined and standard model to organize the knowledge managed by SLAM algorithms. To represent this knowledge related to SLAM problem, semantic web technologies seem to be a good option, especially through ontologies that are able to provide machines with knowledge representation and reasoning capabilities to solve tasks, as well as to allow for semantic interoperability between heterogeneous systems. This is an example of an heterogeneous robot system. We have the presence of two robots with different capacities. The waiter robot, that is a mobile robot, and the chef robot, that is not. There is also a smart fridge that can provide information to the chef robot. Although these robots are designed each one for different tasks and with different abilities, with the semantic web through ontologies, they could work together more easily because they have a standard representation of the knowledge. In fact, many existing works have formulated ontologies to model information related to the SLAM problem, but without a standard and common arrangement. To overcome this limitation, our paper proposes a categorization for the knowledge obtained during the SLAM process, based on existing ontologies and SLAM principles, in particularly for mobile robots. It is obvious that in a SLAM scenario, we have to deal with different types of information and knowledge, considering the description of the capabilities, characteristics, and behaviors of robots, as well as environmental and specific domain information. Our proposed classification considers the following fields of SLAM knowledge. 1. Robot information. 2. Environment mapping. 3. Time information. And 4. Workspace. The first two categories are more related to SLAM results, either to obtain them as the robot sensors or the results themselves, like the maps. The next two categories are more related to the SLAM process, since SLAM is a process whose results are enriched over time and with the inclusion of context-specific information. Now it's time to explain each of the categories with their respective subcategories. We'll start with the first category, robot information, which is related to the information that conceptualizes the main characteristics of the robot, like its physical and structural capacities. Here we have 5 subcategories. The first one, robot kinematic information, is related to robot degrees of freedom, degree of mobility, among others. In the figure, we have a manipulator arm with 6 degrees of freedom. These are represented by the white cylinders. This information is important for modeling the actions that the robot can perform, that in turn allows to consider the navigation of the robot in the space it is discovering. The second subcategory it is robot sensor information. It's about the information that the robot perceives through its sensors. For example, in this image we have a robot with 3 light sensors and infrared sensors too. These are the senses that the robot has to perceive the environment that is going to map. Robot pose information. It is important to consider the information related to the location of the robot, position, and orientation related to its degrees of freedom. Robot trajectory information. For mobile robot, it is necessary to model information of the trajectory and not only consider the first and last position. The last subcategory is robot position uncertainty. In the context of SLAM, there is an uncertainty related to a set of positions where the robot could be. Then, it is important to model actual position as well as this uncertainty as possible position. As we can see in the image, while the robot is moving forward following its estimated trajectory, represented by the purple arrow, the uncertainty error relative to its position, represented by the red ellipses, increases proportionally. The second category is environment mapping, which includes information generated directly by the task of mapping and localization. Here we have 4 subcategories. The first one, geographical information, it is part of the result of mapping, which is a basic requirement for autonomous robots. They must be capable of creating an accurate and in-depth characterization of the surrounding. Hence, it is essential to model the geographical information of the terrain in which they are. Autonomous robots can conceptualize single scenes like offices or multiple scenes like departments. Landmark basic information. It refers to the information related to the presence of other objects in the environment that are not the robot, and the position of these objects on the map being built during the SLAM. For example, in this map, the SLAM algorithm, in addition to recognizing the desktop, also recognizes the objects above it. Landmark shape information. Besides the information related to the landmark position, in some scenarios, it is also useful to know the shape it has, or if it's a complex landmark. For example, this coffee table is composed of the top and open shelf and left and right leg. In some SLAM scenarios, the ability of decomposing landmarks into simpler parts can be useful. The last subcategory, landmark position uncertainty. In addition to the uncertainty of robot position, the uncertainty of the position of landmarks can be considered. That means to model possible positions and actual landmarks position. For example, in this image built by a SLAM algorithm, you can see how the objects on the table are not fully defined, keeping some uncertainty. The third category is related to dynamic environments which can change over the time. It's called time information and has 2 subcategories. The first one, time information of robots and objects. It is about consider information related to poses and position of robots and objects during the time. Like this image on the left. Here we have a robot who changes its position at certain times. Mobile objects, it relates the knowledge of objects that can be present or not at the specific moments in time. In other words, it matters objects with respect to time. For example, on the right we have the result of applying ORP-SLAM in a street scenario. It will be interesting to be able to capture the information of mobile objects, such as cars and pedestrians. The last category is workspace information, which is related to general characteristics that describes the workspace in which the SLAM solution is applied, and also has 2 subcategories. Dimensions of mapping and localization, it refers whether the mapping and localization is modeled in 2D, like the left image, or 3D, like the right image. The other subcategory, specific domain information, is about if the SLAM solution is used in particular applications, where it's important to model high-level knowledge of the environment that surrounds the robot. Example of specific entities or objects that can be modeled could be related to a restaurant, for a restaurant service domain, like the top image, where it recognizes a stove and other kitchen equipment, or it could be in a museum, for a tourism application, like the image below, where the algorithm could recognize the exhibits, paints, as well as the room and the lobby. we evaluate several of the most used ontologies in this domain according to our proposed classification of SLAM knowledge. This group of ontologies was chosen after a detailed review where the starting point was more than 40 research works related to solve the SLAM problem in some way. We selected works from 2010 and some older ones that have been widely cited or represent the basis of more recent projects. The final result was these 19 ontologies, analyzed according to the proposal in this table. It is marked with an X if the ontology models the subcategory associated to the column. For example, robot ontology models the first subcategory of robot information, which is category 1, and the same applies to the other ontologies analyzed. Besides, we want to analyze the application scope of the ontology. We can see that these ontologies are applied in rescue and search, planetary robots, service robots, and so on. Moreover, we also registered if the ontology was a new proposal or if it has a predecessor. As we can see in the table, several of the ontologies are based on not only one, but several previous ontologies. Finally, we see that there is no ontology that fulfills all the subcategories analyzed. In other words, we did not find any ontology modeling the whole knowledge for SLAM. So it is obvious that more research in this area is required to cover the existing gaps. After the analysis presented, we would like to highlight these 3 points. Many existing works based on semantic web have formulated ontologies to model information related to some SLAM aspect but without a standard. It is important to develop ontologies for SLAM because more detailed information can take developers to include high-level reasoning in autonomous robot decisions. And last but not the least, most ontologies are focused on the results of SLAM, like obtain a map and localize a robot in that map, but not in the process of obtaining those results, and that concerns us, because SLAM problem is a continuous problem in time. That means that it's desired that an autonomous robot must be solving it all the time, since it works in a real world and it can find new places at any time. We have parsed the importance of representing the timely information into SLAM ontologies to improve the process of solving SLAM. In conclusion, we propose a classification to organize the knowledge related to the SLAM problem with 4 categories: robot information, environment mapping, timely information, and workspace information. Also, there is not an ontology fully covering the whole SLAM problem. That's why, as a future work, we intend to propose a more complete ontology capable of representing all levels of SLAM information. Thank you very much for your attention. If you have any question, please do not hesitate to contact us.